Hello everyone, I'm Jiaxu Zhao, a PhD student from the Institute of Information Engineering, Chinese Academy of Science. I will share with you our latest research on embedded systems in security. Embedded systems are usually installed on different IoT devices and network devices, and these devices are also throughout our daily life. And its security issues are increasingly important. Vulnerability tech methods for embedded systems are mainly divided into two types. Dynamic methods are less applicable than static methods due to factors such as code coverage and simulation success rate. But for static methods, false positives and false negatives are still the problems. Below we use two real vulnerability examples to show our motivation. The black circle from 1 to 5 shows how HTTP request makes a vulnerability CVE-A. The white circle from 1 to 5 shows the CVE-B. When triggering the two vulnerabilities, the URI field in the HTTP request is handling first, and that the key field is handling next. The difference is that CVE-A has a corresponding front end, while CVE-B does not. But we can still manually construct a HTTP packet for CVE-B to make the vulnerability. So we call this type of data defined only on the backend as hidden data. However, existing techniques have difficulty in identifying vulnerabilities similar to both CVE-A and CVE-B due to the omitted source. For CVE-A, it is mainly caused by the incomplete rules to capture the common keywords between frontend and backend. For CVE-B, it is because it cannot extract hidden data. So we make an observation. First, user input can be divided into URI and key, and there is a corresponding receipt between the two. Secondly, there are hidden URI or key that are not defined in the front end but can be processed in the backend. Finally, different URI or key have similar handling code patterns. So we can get to the first finding. Identifying URIs and keys handling codes and relationships can help to identify both hidden and non-hidden user input attributes and locate the tainted source. And we found there are 4 relationships between the URIs and keys in front end and back end, including hidden and non-hidden data. But convert the founding one to methodology has a challenge that how to identify the backend handling codes. To address the challenge, we think we can conclude some patterns to do static analysis. The detailed automated method is use some non-hidden URIs and keys from the front end to locate the corresponding handling codes in the backend and then extract the other hidden and non-hidden URIs and keys in the backend. However, code patterns still bring some false positives. For example, in the following codes, 2 key handling functions can be identified based on the key extracted from the front end, but one of them is obviously wrong. It's a strong compare. The main reason for false positives is the lack of semantic information in the code. So the second challenge is to combine the semantic information for analysis. To address challenge 2, we proposed the funding 2, where large language models can be used to assist in performing more accurate static analysis. The main reason is that the source of false positives made by LM-IDE analysis and the pattern-based analysis are different. You can see this code example. Based on the 2 findings, we designed Lara, a static analysis tool for embedded systems. It mainly has 3 parts, targeting the 3 stages of data analysis: source instructions, sync instruction, and taint analysis. Source extraction is a cure and it has 6 steps. In general, use the UI or K of the frontend to identify the corresponding handling code of the backend, and then extract the backend keys as a source. There are 2 analysis methods, pattern-based analysis and LMI analysis. We have summarized the code patterns of UI and K in frameworks, among which there are 3 types of URI handling code: registration function, counts data in data segment, and new process creation. And the K handling code has only 1 type. The K in the HTTP request is placed into the corresponding value through the K handling function. For LMI analysis, in order to make better use of the large language model, we designed the models for extracting URI and K based on LMQL, which mainly includes 3 fields: query, from, and where. The query part is the interaction process and the from field specifies the type of the large language model, and where field extracts the answer of the large language model. For detailed promo design and merging operations, please refer to the paper. As shown in the following 2 figures, with LMI analysis and pattern-based analysis, we can mainly reduce the false negatives in URI registration functions and false positives in the K handling functions. You can see the left figure is for UI registration functions, and the right figure is for the K handling functions. For sync extraction, standard library functions and non-function things are predefined, like serial copy, system, and number of controlled loop, and so on. We also analyze the wrapper functions in shared libraries, which was always overlooked. For example, in the following code, there is a risk of command injection when saving data, but its functions, the detailed code is in the shared libraries, so we don't. Sometimes we will overlook it. During Taint analysis, we use K handling functions, argument, or return values as a source, and we record and check the constraints of the tainted data. So, how to evaluate our tool Lara? We designed 3 search questions. The first is to compare with the state of our tools. The second is to verify the effectiveness of each component of Lara. And the last one is to discover zero-day vulnerabilities. For a dataset, we built a dataset containing 203 firmware samples and collected 646 known vulnerabilities to compare vulnerability detection results. The detailed source and sink information of known vulnerabilities are manually confirmed. Baseline includes 3 static analysis tools and 6 different Laras. For search question 1, we can find that Lara has a clear advantage. Compared with SATC and Carrot, Lara finds more vulnerabilities in a short time. Comparing the extraction results of the source, Lara can extract more accurate URIs and keys than SATC. For file comparison, we provide the source and sink to Taint, and the results showed that more vulnerabilities could be identified, and the source and sink provided by Lara were more effective. Also, we make false positives and false negative analysis of Lara. For research question 2, we make an ablation study. First, compare SATC and LARA combined source extraction helps identify 422 more one-year abilities. Among them, combined with LMI analysis, and we can more accurately detect vulnerabilities and extract source by reducing false positives and false negatives. Compare SATC and LARA sync, and compare LARA combined and LARA sync extraction can help detect more vulnerabilities. For Q3, we found 235 unknown vulnerabilities based on the firmware dataset and get 162 CVE IDs. In summary, our tool can effectively improve the taint analysis results in detecting vulnerabilities and perform better than existing tools. The dataset and code will be open source soon. Okay, that's the end of my talk. Thanks for listening.